Hi guys, welcome back. We're starting chapter 14 today, just section 1, and we're talking about matter. Finally, we're getting into some chemistry. All of these elements on the periodic table, that's what all matter is made up of. Okay, so we're going to spend the next couple of chapters talking about that. All right, so matter has these things known as characteristic properties, and basically it's a property that can be used to identify a substance, and it doesn't change no matter what type of sample you have. So for instance, I could have an ice cube, and I could have a snowball, and I could have a cup of water. They all look very different. Those are very different samples of water, but they're all still chemically water. They're still H2O, okay? And in chemistry, we're going to talk a lot about pure substances. I'll define that for you in a minute. These pure substances have these characteristic properties that can be used to identify them, okay? One is the boiling point, okay? Obviously, that's the temperature at which a substance boils, but that is the same. So again, I could stick a snowball into a pot of water. I could stick an ice cube into a pot. I could stick a cup of water in there. I could, any number of things, any number of types of water samples, they're still all going to boil at 100 degrees Celsius, okay? What that also means is that you can kind of determine what state of matter something is going to be in based on its boiling point. For this table right here, I'm giving you the known boiling points of certain substances. Let me get my pen. Okay, so typical room temperature is about 20 degrees Celsius, okay, roughly. It's about 70 degrees Fahrenheit. So what that means is that you can compare the boiling point to that temperature. So water, obviously at room temperature, is much lower than its boiling point, which means it's going to be a liquid, okay? Butane boils at negative 0.5 degrees Celsius, which means room temperature is well beyond, it's much hotter, it's much higher than its boiling point. So that means it's already boiled, okay, which means it's a gas, okay? So this will be a liquid, this will be a gas, this will also be a gas because the boiling point is so much lower than room temperature. That means that we've already hit its boiling point, okay? But pentane needs to reach 35 degrees Celsius in order to boil and then become a gas. 20 degrees is not enough, okay? So it would also be a liquid, and then finally methane would definitely be a gas, okay? Meaning it's already boiled, it's already changed from its liquid to its gas state, okay? Well, we also have the melting point. That's temperature at which a substance melts. Now you can use the melting point and the boiling point as kind of bookends. And if the temperature, if you get your room temperature kind of as your base point there, you can determine what state of matter a sample is going to be in. If room temperature is higher than its boiling point, it's going to be a gas. But if room temperature is right in between that boiling and melting point, it's going to be a liquid. If room temperature is below that melting point, that means it hasn't melted yet. That means it's going to be a solid, okay? So I have an assignment for you. Yes, you need to watch the videos to get some of these assignments. I need you to go to page 440 and look at the sharpen your skills there. There are 5 different substances on that list. You're given the boiling point and the melting point. You need to tell me the state of matter that each of those things is in at room temperature. And just stick it in an email, message me on Edmodo, whatever. 5 different substances. Are they a solid, a liquid, or a gas based on their characteristic properties of boiling and melting points, okay? We have a couple more characteristic properties. Density is kind of a characteristic property, but within its state of matter, okay? So again, using water, the density of water will be slightly different between a solid, liquid, and a gas, obviously. But if I have any liquid sample of water, the density is going to be the same. If I have any solid sample of iron, the density is going to be the same, okay? It doesn't matter how much or how small of a sample I have, the density is going to be the same and can be useful for identifying that substance. And then finally, the chemical activity of a substance, basically how reactive it is or what it reacts with, okay? All right, so let's talk about these changes in substances. We're going to talk about physical changes and chemical changes. A physical change simply alters the form, but not the chemical identity of the substance itself, okay? So, well, I'll give you some examples in a minute, okay? Any change of state is considered a physical change, okay? An ice cube and liquid water are both still H2O, okay? Tearing paper, okay? Whatever the chemical formula for paper is, it's got a lot of cellulose in it and whatever else, okay? The chemical composition of this whole piece of paper is the same as it is each individual piece, okay? So I've changed the paper, it's obviously different, but that's just a physical change. I haven't chemically changed it. Chopping wood, breaking a pencil, things like that, and mixing things. This one's a little more confusing, but if you just take like Country Time lemonade powder mix and you dissolve it in water, it looks like a different substance, but it's still chemically the same. The sugar is still in there, the flavoring is still in there, the water is still H2O. You haven't actually done any kind of chemical reaction to chemically alter things. You've just made a mixture, and we'll talk about that a little bit later. All right, let's talk about chemical changes. A chemical change is when one or more substance combines or breaks apart to create a totally new substance, okay? It's also called chemical reactions. So if I were to hydrolyze water, which means break apart water, I would separate that H2O into its hydrogen and its oxygen. And hydrogen and oxygen are totally different separately than they are combined into H2O, okay? Hydrogen is an explosive gas, and water is super stable, okay? So putting those two things together or breaking them apart would be an example of a chemical change. Burning anything, okay? Now I can take this match and I can break it. That's a physical change, okay? But if I take a match and I light it, okay, that's a chemical reaction that's happening, and it's altering the chemistry. So the stuff that was on the end of that match is now different, and it's releasing energy as heat. The wood is also changing. You see the wood, the end of the match there, turning black, okay? That is a chemical reaction. So those are chemical changes. The end of the match is now chemically different than what I started with, okay? Mixing baking soda and vinegar. When you mix baking soda and vinegar, you release all these bubbles. That's why it gets foamy, okay? Well, the bubbles are filled with carbon dioxide. Baking soda is not CO2, vinegar is not CO2, but they both contain carbon and oxygen, and when that chemical reaction takes place, those recombine and form carbon dioxide. And so you're no longer left with baking soda and vinegar, you're left with carbon dioxide and water and some other stuff, okay? Baking, cooking eggs, heating things oftentimes changes its chemical composition. It changes the protein structure, and so baking is considered a chemical change as well. And so is decomposition. Digesting food is a chemical change, and the decomposition of organic material breaking down is a chemical change, okay? All right, so let's go back to this idea of mixtures. Matter can be classified as mixtures of substances or pure substances, okay? All of these things up here are pure substances. If some of these things are chemically combined together, it's still considered a pure substance, okay? But sometimes they can just be mixed and not chemically combined, okay? So when two or more substances are kind of stirred together or mixed, that's not considered a pure substance, but it's also not a chemical change, okay? And then a solution is just that best possible mix. So the Kool-Aid there, yes, the Kool-Aid that I use to color my hair, is a mixture. It's a very good solution. If you just dump the Kool-Aid into the water, it's all going to sink to the bottom. It might color the water a little bit and create somewhat of a mixture, but you need to stir it and stir it and stir it to get all that Kool-Aid to dissolve and create a solution. Still not a chemical change, not a chemical reaction, okay? The chemical composition of Kool-Aid and sugar is still there and identifiable, The water is still H2O, even though it tastes sweet and it's now red, okay? So again, those would be physical changes, not chemical changes. All right, now let's talk about the pure substances. They are made of only one kind of matter, and that's where these characteristic properties come from, okay? Now, it doesn't mean only one element, okay? H2O, water, is a pure substance. Sugar, glucose, carbon dioxide, salt. You can chemically combine a whole bunch of these elements, and that's still going to be considered a pure substance, and it's going to have those characteristic properties, okay? Now, elements, these individual substances up here, those can't be broken down into any other substances. So any individual element on the periodic table, sodium, chlorine, hydrogen, oxygen, whatever, those are elements, okay? And the smallest piece of an element you could have is called an atom. You can break atoms down into smaller parts, but once you, like if I have a single atom of nitrogen, it's identifiable as nitrogen. If I break that atom apart, it's no longer going to be considered nitrogen, okay? So that a single atom is the smallest piece of an identifiable element that you can have, okay? Well, we can mix those elements. We can chemically combine them, chemical changes. And those, again, they'll still be considered pure substances. We call them compounds now. So I took the sodium and the chlorine and made sodium chloride. That's table salt, okay? Now, sodium by itself is a very soft metal that when you combine it with water, it explodes. It catches on fire. Chlorine is a gas that if you breathe it, it'll kill you. On their own, they're both very, very reactive and very dangerous. But once they've chemically combined into salt, I mean, it's just good on French fries, and it's safe. I mean, you can have too much and cause heart problems, but that's a different story. Again, I talked about hydrogen being an explosive gas, but when it's combined with water, it's totally, totally stable and totally safe. This is actually table sugar. This is a very complicated compound, but it's still considered a pure substance, okay? Sugar will have those characteristic properties and known characteristic properties to help identify them, okay? The very smallest piece of a compound you can have is called a molecule. So kind of those word analogies that you get on standardized tests, an atom is to an element as a molecule is to a compound. Those atoms and molecules are just the smallest piece of those things that you can have, okay? That's it. I felt like I talked a mile a minute. I hope you followed along, do your homework, and I'll see you soon.